Hi, I'm Kirti. I'm going to discuss about determination of equivalent circuit of a three-phase induction motor. Induction motors are by far the most used electromechanical devices in industry today. Induction motors hold many advantages over other type of motors. They are cheap, rugged, easily maintainable, and can be used in hazardous occasions. Despite its advantages, it has one more disadvantage. It draws reactive power from the source to be able to operate, and therefore the power factor of the motor is inherently poor, especially under starting conditions and under light load conditions. To improve the power factor, reactive power compensation is needed. Where reactive power is injected, several techniques have been suggested, including synchronous compensation, which is complex and expensive, switched capacitor banks, which requires expensive switchgear and may cause voltage regeneration, over voltage, and high inrush currents. Arbitrary reference frame theory is mainly used in dynamic analysis of electrical machines. Because of the highly coupled nature of the machine, especially the inductances within the winding, make it rather impossible to perform dynamic simulations and analysis on the electrical machines. By using this method, a polyphase machine is transformed to a two-phase machine with their magnetic axis in quadrature as illustrated in the figure. This method is also commonly referred to as DQ method in balanced system and DQ naught method in unbalanced system, with the referencing to zero sequence or homopolar component in the transformation. The transformation is done by applying a transformation matrix equation. While the inverse transformation matrix will transform back to the natural reference frame, it applies to a three-phase system but can be modified to accommodate a system with any number of phases, which might be useful in the case of machine having an auxiliary winding as proposed in this work. Coming to the modeling of three-phase induction motor, the winding arrangement of a symmetrical induction motor as shown in the figure. The stator windings are identical and sinusoidally distributed, displaced 120 degrees apart, with NS equivalent turns and resistance RS per winding per phase. Similarly, the rotor windings are considered as three identical sinusoidal distributed windings, displaced 120 degrees apart with NR equivalent. In developing the equations which describe the behavior of induction machine, the following assumptions are made. The air gap is uniform, eddy currents, friction and windage losses and saturations are neglected. The windings are distributed sinusoidally around the air gap. The windings are identical. The voltage equations for each winding on the stator and rotor can be determined by stator winding and rotor winding. A, B, C referring to the phases, S referring to stator variables, R referring to rotor variables, V referring to instantaneous voltage, I refers instantaneous current, and lambda referring to flux linkages. After obtaining the voltage equations in the natural reference frame, the transformation to arbitrary reference frame can be done. Ks is the transformation matrix and Ks inverse is the inverse transformation matrix for the stator parameters. Kr is the transformation matrix and Kr inverse is the inverse transformation matrix for the rotor parameters. Equations yield the flux linkage in the arbitrary reference frame. Comparing equations, it is clear that theta r has been eliminated from the flux linkage equations by using the arbitrary reference frame transformation. It means that the flux linkage is no longer a function of rotor position. The set of equations is completely once the expressions for the flux linkages are determined. Substituting the equations of transformation into the flux linkage equations expressed in ABC variables yields the flux linkage equations for a magnetically linear systems. The voltage and the flux linkage equations suggest the equivalent circuit shown in the figure. Since machine and power system parameters are generally given in ohms or in per unit of a base impedance, it is convenient to express the voltage and flux linkage equations in terms of reactance rather than inductances. Substituting for currents into yields the voltage equations in terms of flux linkages per second, it is interesting to note that each Q and D voltage equations contains two derivations of currents when currents are selected as independent or state variables. When flux linkages are selected as independent variables, each Q and D voltage equations contains only one derivative of flux linkage. This property makes it more convenient to implement a computer simulation of an induction machine with flux linkage as state variables rather than with currents. Thank you.